We'd like to begin and get back on track here. We have a presentation now from Nvidia on GPU. Dale Southard. Southard. Okay, sorry. I apologize.
Close enough.
All right.
First off, can everybody hear me? If I just stand here, or do I need to go all Elvis?
Okay, sounds good.
Okay, excellent. Since this is an interconnect crowd, I thought I'd start with a little bit of background in the GPU programming model for those that haven't used them. So on a typical GPU node, you'll have two types of processors. You'll have CPUs, your standard AMD or Intel processor, optimized for low latency, so it's got deep caches. It has a lot of control logic for things like out-of-order execution. And some number of ALUs or cores. I believe Intel just announced 10 cores, and we've got some 12-core entries from AMD. So that's the CPU, optimized for low latency. You also have GPU processors. GPUs are optimized for data parallel high throughput. So they're latency tolerant. They do not have very deep caches. In both cases, you have latency from main memory. In the case of the CPU, you try to hide that latency by having a large cache between you and main memory. In the case of a GPU, you don't have large caches, but what you do have is the ability to launch a lot of threads. So you hide that main memory latency by launching lots of threads. Our current top-of-the-line GPU has 448 cores. Typically, to saturate that device, you're launching a few thousand threads. The GPU schedules threads using hardware rather than a software model, so it essentially just picks threads that are ready to run, schedules them to ALUs, and lets them execute. The advantage of that is you can, when you don't have the caches and the control logic, you can pack a lot more cores on the same piece of silicon. The disadvantage when it comes to things like what you guys do in Open Fabrics is that you have two memory spaces. The CPU has its own memory with deep caches. The GPU has its own memory that's more parallel to keep its larger number of cores fed. The problem is that the message passing is all happening on the CPU side, but the majority of the flops, the majority of the processing power in those nodes comes off the GPUs. A single top-of-the-line NVIDIA GPU today has about 515 gigaflops raw double precision performance. So, and typically in most installs we see usually 2 or sometimes 4 and now going to 8 GPUs per node. So there's a lot of flops attached to the GPU memory, but it's on the wrong side of the PCI Express fabric to work with MPI. The big problem becomes that for efficiency reasons, you want to use pinned memory when you're doing DMAs to the GPU or RDMAs to the Infiniband or other fabric card. In the case of the GPU, our driver for CUDA allocates its own pin memory region for DMA transfers. So when you're using CUDA host alloc or CUDA malloc host, that's actually allocating a pin memory region on the host for the GPU to use for DMA transfers for best bandwidth. The IB driver wants to do the same thing. So if you've got Infiniband, you want a pin memory region so that you can DMA more efficiently or RDMA out to another node more efficiently. The problem is that these two drivers have no knowledge of each other's pinning. So if you allocate something through the GPU driver and it gets pinned, the IB driver has no knowledge of that pinned region and has to assume that it's not pinned and then goes through a slower path. The same for the GPU. If you RDMA something into a pinned region over the IB card and then attempt to push it to the GPU has no knowledge that that region is pinned, so it has to use some fallback methods that are slower, and you lose about 50% of your bandwidth. And to cap it off, the MPI stack has no knowledge whatsoever of the GPU. So our first effort at fixing this is something called GPU Direct. So here's what the transfer picture looked like before GPU Direct. If you were trying to get an efficient transfer to the GPU, from the GPU out over IB, you would essentially do a DMA from the GPU across the PCI Express bus and the chipset into main memory. You would do a mem copy in main memory from that pinned region to a pinned region that the IB driver was aware of, and then the IB driver would do an RDMA out to another node. So you ended up with 2 copies of the data in host memory, and you had to do a mem copy or a blit to move the data in between those 2 buffers. So, as I said, our first pass at fixing this is a technology called GPU Direct. GPU Direct we really use as an umbrella term for trying to improve interoperation with third-party devices. And for HPC, especially third-party devices that are being used as a cluster fabric for MPI messaging. The long-term goal is to make the GPUs more autonomous. Try to free up the CPU. So instead of having the CPU kind of shepherding all these transfers for us, the CPU is kind of left to its own devices and isn't necessary for the GPU to function. GPU Direct contains both some programming model changes and some software enhancements, and at the moment it's Linux only. So GPU Direct V1 is something we worked on last calendar year. We jointly developed it initially with Mellanox. It was kind of our first attempt at working with a vendor that makes a different kind of hardware that's also on the PCI Express bus. What GPU Direct does is provides a mechanism for the IB driver and the CUDA driver to share a pinned memory region. So it's a small kernel patch that provides some essentially mechanisms for registration and a callback, and it allows you to allocate memory through our driver path that's pinned, and then have the IB driver become aware of that pinning, so that it knows the PA and doesn't have to assume that it's non-pinned memory. And we also, of course, have to guarantee proper cleanup at process shutdown, since you have 2 different drivers pinning the same region. So that's been shipping for quite some time. It's available on Mellanox's website. With GPU Direct V1, the picture changes like this. So now you can do a DMA from the GPU out through the chipset into host memory on the CPU side, and then from that same buffer you can RDMA out without having to do a copy or to use some fallback mechanism that assumes the memory is non-pinned. So that's where we were up until a few weeks ago with the release of CUDA 4.0. So CUDA 4.0 really is kind of the first major CUDA release where we're trying to address some of these things directly in our driver and toolkit stack. So we've brought a number of technologies in that should be of interest to people that are doing RDMA type fabrics, and should provide some performance enhancements as well as a path forward to better performance in the future. The first of those is no copy pinning of system memory. As I mentioned, we provide a couple of functions, CUDA malloc host, CUDA host alloc, that allocate memory that's pinned. So with CUDA 4.0, we're also providing a way to take a regular pointer to virtual memory and register that with the driver so that it's pinned, or so that the driver's aware of it. So you can, with no copy pinning, you essentially do your malloc, whether that's done through regular system or through some IB-specific mechanism. And then you call CUDA host register on that pointer to register that with our driver, indicating that it's a pinned region. You then do your normal GPU computing runs, so you do transfers to or from the GPU, you launch kernels, etc. And then when you're done, your application calls CUDA host on register. This works on all CUDA-capable GPUs. It requires kernel 2.6.15, and it's shipping now as part of the CUDA 4.0 release candidate. So what no-copy system pinning essentially does is let you do the same type of thing that you would have done with GPU Direct, but does not require GPU Direct v1 and does not require the kernel patch. It's strictly a change in user space code to call the register and deregister routines so that our driver is aware that you have memory and is pinned. The second, perhaps more intensive change that we did in CUDA 4.0 is unified virtual addressing. So we're providing one address space, one virtual memory address space for all memory, CPU, and GPU. Additionally, we're providing some introspection routines that allow a program to examine a pointer address and determine whether that pointer dereferences to memory that's on the GPU or memory that's on the host. This is supported on Tesla 20 series, so basically Fermi GPUs. Note that I said unified virtual addressing, not unified virtual memory. We are explicitly not unifying the memory. You still have two separate memory spaces, memory space on the GPU that's optimized for parallel transfer and throughput, a memory space on the CPU that has deep caches. But what we've done is unify the virtual address space so that a given pointer cannot alias. If you have a pointer value, it's either dereferences on the GPU or dereferences on the CPU, but there's never an alias where the same pointer could be dereferenced either place. So we're not doing any data movement for you. You still have to explicitly do data moves, but we are providing or are eliminating pointer aliasing. So for those that need a picture, on the left you see what it looked like before CUDA 4.0. Each GPU, and for that matter the system memory, each had their own virtual memory space. With UVA, we're mapping all those virtual memories together. So at startup, when our driver loads, it essentially reserves a chunk of the virtual address space in each process for each GPU memory that you have loaded on the system. So that if you've got some pointer value, that pointer is either valid in system memory or it's valid in GPU memory, but you'll never get a value that's valid in both places. So, the availability of UVA and the elimination of pointer aliasing allows us to do some smarter things with pointers now. And the first of those is what we're calling GPU Direct version 2. So it harnesses UVA under the covers, because remember now we've eliminated pointer aliasing. And it allows you to modify an MPI stack such that the MPI stack is now GPU aware, meaning that when the MPI is doing a receive, it can look at the value of that pointer and make a call to introspect whether that pointer points to system memory or to device memory on one of the GPUs. And then the MPI can, behind the scenes, do the right thing. So for instance, if it's doing a receive, it can set up a bounce buffer in the host, do the receive, and then push it directly to the GPU without requiring the user to explicitly do the copy after the receive. Likewise for sends. Again, we have not unified the memory addresses, we've just unified the virtual address space. That doesn't actually, currently that doesn't actually change performance, right? You're still having to do the copy, but what it does let you do is change the programming model and make it a little bit more friendly. The data path, the data flow is still the same as it was in V1, but now you can start treating GPUs more like full MPI citizens that can receive, and send data directly from their memory, even if behind the scenes we're kind of using the host memory as plumbing. Again, shipping with CUDA 4.0 and UVA support, 64-bit only, and Fermi only. So again, here's the picture for those that need a visual. Transferring out over Infiniband, the data flow is the same. We're still copying to a bounce buffer in host memory and then doing an RDNA out over the Infiniband card. But what the user sees is a direct transfer. So we're allowing users to move their code model even if the performance model hasn't changed yet. So another thing GPU Direct did, if you looked at those earlier diagrams, is not only did we give the host and the device memory mutually exclusive virtual memory address ranges, we also gave each GPU its own address range. So for GPU Direct v2, if you were doing a multi-GPU calculation on a node, and at the end of that calculation you needed to exchange some data, for instance like a Halo exchange in reverse time migration, that required a copy out into main memory. So you would copy your Halos out to host memory, and then you would copy them back into the other GPU. So now that we have, oh, it's got an animation, who knew? Now that we have unified virtual address space, we already had features in our GPUs that allowed bus mastering. We can now expose that. So with GPU Direct v2, you can now do a CUDA mem copy directly from one GPU to another GPU without going through host memory. It's essentially a peer-to-peer copy over PCI Express. So for multi-GPU nodes, again, we're providing more autonomy, less reliance on the host system, which frees up the host CPU to do other things. Advantages of P2P. So it's a direct communication between GPUs. So we have two DMA engines on our GPUs. We're able to saturate PCI Express in both directions. It's a direct transfer. It's not bouncing through host memory. It's actually going directly across PCI Express. This works transparently with UVA. It's direct access if you're doing a read, so you're actually able to DMA out of memory from another GPU using the P2P protocol and load store. And again, supported only on 64-bit Linux and Windows with TCC, and only on Fermi or T20 or Tesla 20 series. So obviously we have some protocol that's allowing us to bus master between GPUs. So some of the future directions we're looking at in things in GPU Direct are, can we extend that protocol to other devices? We're actually talking to a lot of different hardware vendors at the moment on what the capabilities of their hardware are and whether it's possible to integrate our P2P protocol into their hardware. So you could envision with an appropriate IB card, you'd be able to do a direct P2P from GPU memory directly as a DMA write into the IB card. And presumably affecting an RDMA transfer out to another host. Same for storage. There's multiple flash vendors that we're in discussion with that have PCI resident flash solutions that are interested in the same technology. Can they bypass host memory and go directly to and from the GPU without requiring any intervention by the CPU? Additionally, extended PCI topologies. As I mentioned, most of the deployments now are with either 2 or 4 GPUs per node. The China systems are 1 GPU per node. That's due to what they're working on. Most of what we're seeing right now is 2 GPUs per node. Multiple vendors have systems in the works that go to 4 GPUs or beyond in a single node. And again, more GPU autonomy and better NUMA topology discovery, exposure, and exploitation. Questions on GPU Direct before I switch gears for a second? Okay. I've added a... Sure, I'm sorry.
PTP protocol is something
So the question was the P2P protocol, is it Nvidia only? So the P2P protocol was pre-existing for us, meaning we already used it for other things in the OpenGL and DirectX realm. We are opening it up to select hardware vendors, but I would characterize it as early in the discussion. The intention certainly is to share it with vendors that have hardware that can use it, because it helps both us and the vendor. But it isn't a it's pretty specific to our hardware, and I don't think it's really a standards track. So it goes over PCI Express, so it is a peer-to-peer busmaster transfer, but there's you have to layer a protocol over that. GPUs actually are MMU backed; they're not just memory sitting out on the PCI Express bus. Given the audience, I wanted to cover that last bullet point a little bit on NUMA topologies. In discussions with at least one of the Open Fabrics gentlemen, there's been kind of I won't say it's a concern, but one of the things that gets bounced around is, PCI Express is really slowing everybody down. Can't we do something different? Like, can we get these SerDes and these GPUs directly on some kind of fabric that is not PCI Express? So what I'm going to present you is a couple of slides on benchmarking that we've been doing for transfers to and from host memory. So the first one is a dual socket, single bridge design. So it has two processors. I won't mention vendors, and it actually doesn't necessarily matter. And what I've labeled as chipset is really the PCI to memory fabric bridge. So it's PCI on one side, it's either hypertransport or QPI on the other side. On the left, you see the bisectional bandwidth for a bidirectional transfer, meaning we get about 11 gigabytes per second, adding both write to host memory and read from host memory, if we are writing to memory that's controlled by one of the CPUs and reading from memory that is controlled by another CPU. So single GPU using both DMA engines, doing a read and a write simultaneously, but the read is going to memory that's controlled by one socket, the write's going to memory that's controlled by another socket. On the right, you see what happens if we go to the same socket. So the bottleneck there isn't the PCI Express, because the PCI Express part is really the traversal from the chipset to the GPU, and that shouldn't have changed between those two moves. What did change was we're now reading and writing from the same memory controller in the same socket.
Is there a little test built into your code or whatever that we can run ourselves? It's like Heat Tool used to do it with Vericom and stuff like that.
So the question is there a tool that's built into our software that does that? The answer is, in the SDK, we provide an example called bandwidth test, which I hate to call it test because it does have some deficiencies. It's not tuned for Fermi. If I recall right, the labels are incorrect. I think it actually is measuring gigabytes but reports gigabytes, or there's a power 2, power 10 confusion in the labeling of the output. But yes, we do provide some example code to do this move. So this is the first topology concern that On a dual socket system, you really only get max bandwidth if you're reading to one socket and writing to a different socket. If you're going to and from memory in the same socket, you take a performance hit. Adding a second bridge, a second PCI to memory fabric bridge, makes things even more interesting. These are unidirectional transfers now. This is a read from GPU memory into host memory, or a write from GPU so it's device to host. In a dual bridge configuration, we lose about 25% of the bandwidth when we're going from a GPU to memory that's controlled by another socket. So the reason that's interesting, right, is that numerically the bottleneck really should be the PCI Express bus. The memory bus is much faster. But for whatever reason, we don't see that performance. The bottleneck seems to be on the memory side of the bridge chips. The reason you guys are interested is because, you know, we're already at 16 lanes of PCI Gen 3 or Gen 2. We'll be at 16 lanes of Gen 3 once Gen 3 is widely available. You guys are only like one multiplier behind us. So IB cards currently a 40 gigabit IB needs 8 lanes of Gen 2. As you go to FDR and EDR, you're going to be pushing the same bandwidths that we're pushing, and you're going to hit the same bottlenecks that we're hitting. If people that are interested in the topology and bandwidth stuff, I actually have some example code. You can come find me afterwards and give me a business card or send me an email. And I can send you some example code that actually does a lot more complete bandwidth mapping of the host. What we're hoping for actually are things like the portable hardware locality lib that the open MPI guys have built. The hope is that as that matures and they add PCI Express into it, that we'll at least be able to map some of these NUMA topologies a little bit better so that people can program around them more effectively. At least that's the hope.